Hey, this is Jonathan Templin. I'm back with another lecture for the multivariate class. This is a lecture about two particular classification methods from a larger set called mixture models. Specifically, we're talking about latent class and latent profile analyses. And again, this is just an introduction to the idea of classification methods that are out there. There's plenty more. You can have an entire subject, a class on this subject. We'll just dive in a little bit with these to begin with. So today we're going to talk a little bit about both of these methods, and for both we'll talk about their underlying theory, and we'll give an example analysis in R using a couple different packages. For LCA, we'll use the PO-LCA package, and for LPA, latent profile analysis, we'll use the tidy latent profile analysis, LPA package. You'll see there's a lot of similarities between the two. In fact, the methodology is largely the same. The only thing that differs between the two is that by previous or initial definition, latent class analysis is for binary data, whereas latent profile analysis is for continuous data with the assumption that you basically have mixtures of multivariate normal distributions. So you'll see a lot of similarities between the two of these methods. All right. So we'll first start by starting with a couple bits of definition here. First, clustering versus classification. So you may hear a researcher mention cluster analysis. There are so many methods involved in that. They could mean many different things. K-means clustering, hierarchical clustering using what we call distance methods, discriminant analysis methods, and something called taxometrics. And that's only just some examples. There's even more of that now in the world. Much less often, though, latent class analysis is included in this group. It's a model-based approach where the classes themselves take the form of latent variables. And so this being a lecture that just came after us talking about latent variables for several weeks, this is a good place to include them. It's also latent class analysis, latent profile analysis are also good for detecting clusters of observations. And so for this lecture, we're going to consider clusters and classes to be synonymous. Typically, when you hear these two, clustering is often used for the process of finding clusters, whereas classification is typically used as a word to describe placing objects into those known clusters themselves. But for today, keeping things high level, we're just going to consider these to be synonymous in this lecture. So although we use the terms classes and clusters synonymously, latent class analysis does differ from those other methods that you saw on the previous slide. In particular, latent class analysis is a model-based method for clustering. It fits a statistical model to the data to determine the number of classes. And actually, we fit a series of models to determine the number of classes. Other methods, such as k-means or hierarchical clustering, don't explicitly state a statistical model. Some of them have implicit models that you can show they're related to, but that is a difference between the two. So with our methods being model-based, that means we can make explicit testable assumptions about our data, assumptions that can be checked against the observed data themselves, very much like you saw in path analysis, structural equation modeling, measurement model section of the course, where we would have a model, we would say what it should show the data looks like, and we'd have methods for testing whether that model fit the data itself. So let's get into latent class analysis first. Latent class models are commonly attributed to the work of Lazarsfeld and Henry. There's a great book from 1968 on the topic. The way these models are used is that the number of classes in your data, or clusters in your data, are not predetermined prior to the analysis. So very much like exploratory factor analysis, where you seek to find how many factors, and then once you determine how many factors, try to understand what those factors represent. In latent class analysis, you seek to find how many classes you have in your data, and then seek to figure out what each of those represents. So this is similar to the other methods, k-means, hierarchical clustering, in terms of first, figure out number, second, figure out what they mean. The variable types used in latent class analysis, as originally conceived, are a set of binary variables, typically coded as 0 or 1. So these could be test items. The example we use today is from a paper looking at classifying students based on answers to 4 questions on a test, scored correct or incorrect. But these could also be true or false questions, or any other binary outcome you might have. There are, of course, extensions to LCA. So just like you saw with generalized linear models, where we just change the type of distribution for our data and we can fit different data into our model, same thing works for latent class analysis. We may have more than two categories, and so therefore we might use an ordered logistic regression in this analysis, or order basically a multinomial or categorical variable. We may also have nominal indicators as well too. Basically, the idea is that this methodology, which latent class analysis falls under this bigger heading of finite mixture models, is just like in other fields, we can change out the distribution of the data and use different types of data with the same methodology. Now, latent class analysis is a term that's specific and general at the same time. In researcher speak, you may hear someone say, I did a latent class analysis, and it may not refer to specifically binary outcome variables. And that's because the word latent class analysis has taken on lots of meaning, kind of like if you want to send something quickly, you FedEx it. Well, FedEx is one of the companies. There are plenty of companies out there that will send things for you. Latent class analysis, as written by Lazarsfeld and Henry, literally was about binary variables themselves. So that's sort of a distinction, and that's how I'm going to try to use this today. But when you hear people say latent class analysis, they really typically are referring to some type of finite mixture model where the mixture model itself is in place, which we'll get into in a few slides. But the distribution may be something other than Bernoulli for your binary data. So the process is very familiar, particularly mirrors that of exploratory factor analysis. What we end up getting for once you set the number of classes, for a given model, you have to pick how many classes are in it. So once you set that, the model will give you, for each class, the probability that each indicator, each observed variable, equals 1. So this is the probability a person from that class answered that item with a 1. And then for each observation, we're able to get the probability of belonging to each class. We'll use alpha to denote that. Right? So this means that observations in our data are classified into classes without certainty, with uncertainty, which is actually helpful. This is a little bit different than k-means clustering, where class membership is certain. It's basically you can define someone being part of a class based on how close their data are to the center part of that class or the data in that class as well. We also can receive one other bit of information. That's the probability that any observation at large from our sample is within each class. We use the eta sub c to define that. So latent class model estimation differs from other clustering methods in that we have these distributional assumptions that help us guide us towards more maximum likelihood-based solutions. Now, the other methods I had mentioned before, k-means and hierarchical clustering, don't really use fancy estimation. They sort of iterate between ways of determining whether people are in classes and then which classes happen to be. For latent class analysis, though, we use the EM algorithm, which is a version of maximum likelihood, something we call marginal maximum likelihood. The marginal refers to estimating the likelihood function by marginalizing out the class variable from it itself. So EM stands for expectation maximization. There are multiple iterations of the EM algorithm, so it's an iterative algorithm, just like maximum likelihood would be. But within each iteration, we have a cycle between the E step and the M step. And the E step is what we use to create posterior probabilities for each person. So the E step allows us to plug in the expected value, in this case, a probability that person is in each class. And then conditional on those probabilities, we flip to the M step, where we maximize the log likelihood given that cycle, given that iteration of our analysis. So we keep iterating between E and M step until we get very close to where our log likelihood doesn't change. And at that point, we call the analysis converged, and we look at our results. We hopefully get through convergence. Sometimes these models have a hard time converging, particularly as the number of classes grow. Now, latent class analysis and finite mixture models in general suffer from a couple different pitfalls, one of which is the likelihood function itself is not single-peaked. That means there's no one given maximum, potentially. And that's difficult. It works very different from the models you've seen estimated with maximum likelihood before. So what that means is we have to usually start our model at multiple random starting values so that we can determine whether or not the maximum that we've received is the maximum overall. Now, we still never can determine whether we have a maximum, but if we start our model, let's say we run our model 100 times, each with a different starting value, then we look at the log likelihoods. If we see that one of our log likelihoods is the highest, that would be the one that they would settle on. This is a bit unsettling from the maximum likelihood approach, given that the maximum likelihood point estimates have the good properties. And if you're not at the maximum, you're not guaranteed to have those good properties: asymptotic convergence, asymptotic consistency, and asymptotic normality. So it's a little bit difficult. These models are a little bit difficult to work with. Okay, let's get into how these models are estimated, how they function. As mentioned before, the latent class analysis uses binary outcome variables. So we need a binary outcome distribution. And with each, so we've seen this before. In fact, we had a lecture on logistic regression previously. And we're going to use the same distribution that we assume in a logistic regression, that is a Bernoulli distribution. So Bernoulli distribution is a categorical distribution where the data can take two categories, a 0 or a 1. And the way the distribution the probability density function, actually in this case a probability mass function because it's a discrete distribution, is as follows. The basically the this pi parameter is the only parameter of the distribution. It's the probability of a 1 rather than a 0, raised to the actual outcome itself. X in this case can be a 0 or 1. So when x is a 1, the probability of 1 happens to be pi, because this part goes to 0, meaning this other part of the distribution becomes 1 itself. So when x is a 0, this part goes away, and we're saying the probability of 0 is the complement, 1 minus the probability of a 1. So that's Bernoulli distribution. So we can think of it this way. Let's imagine the probability of a correct response to one of these math items in our example that we're about to get into is 0.75. So we'll say an x is 1 if a student answers the question correctly, and x is 0 if the student answers incorrectly. So now we would say if x equals 1, the likelihood, remember the probability density function gives rise to a likelihood itself. The likelihood in this case would just be that probability 0.75. If it's x is 0, the likelihood is 0.25. So for discrete outcome variables, the likelihood itself equals the probability of the event occurring. Now, oftentimes we just call this probability because in discrete distributions that is the probability measure, but we can think of it as likelihood as well. It is the basis for the likelihood function. So what we assume in a latent class analysis is that within a given class, the Bernoulli variables or the observed data themselves are independent, which means we can then form a joint likelihood for a person based on the product of each of the variables, PDFs, right here. So this product term assumes independence. This is very similar to the assumption of local independence in psychometric models, meaning conditional on class membership. Knowing one item response gives you no other information about the others, or another way of putting it, the classes themselves, the class structure, class variable, is the reason why items may be correlated in the first place. Just like the latent variable in a psychometric model is why the observed items may be correlated themselves. So what this is assuming is that any association, any non-zero correlation among these observed variables is explained entirely by the latent classes that the people will fall into. Now, the finite mixture model itself takes this Bernoulli distribution, this would be a distribution for one class right here, and inserts it into a larger marginal likelihood function. By margin, what we're talking about is we're integrating over the space, or in this case, summing over the space of the classes. In this case, G reps for group or class itself. So the marginal likelihood, the Bernoulli part, was the section in this likelihood function, and now it becomes dependent upon the class variable G right there. If I go back a slide, you'll see this section. That means that now each one of these parameters is specific to each of the classes. So I put a G here. This is pretty funny trying to draw with my finger here. There we go. Class G right there. So the marginal likelihood basically weights each class likelihood by the probability of persons in that class at large. That is what we call a mixing proportion. It functions also like a prior distribution in the Bayesian sense. It sort of talks about the probability or the base rate of people falling in a class overall. So you get two parts of this model. You get a measurement part, right, where the classes meet the latent variable. In this case, I'm sorry, the latent variable is the class, and the data meets the latent variable. That's this measurement part right here. You get a structural part right there, which weights the measurement part by how likely a person would fall in a class in general. The model itself will estimate each one of these terms. Get rid of my drawings. So therefore, for what we end up doing is we sum this for a given person with J variables and C classes. This is the overall finite mixture model likelihood function, marginal likelihood function for this one person I itself. So now this is interesting. What this gives us is the overall probability of the data themselves, right? What it's broken into is the probability a person falls into each class totally. So what we have to do in our estimation process is answer these two questions. First, how many classes are present in our data? Right. So what we will do is fit a latent class model with different number of classes, 1, 2, 3, 4, 5, etc. And then based on relative fit indices, such as AIC and BIC, absolute fit indices, such as chi-square and entropy, we will try to pick the solution that seems to fit the data best. Then what we will do is look at what each class tries to represent. So we'll go back and look at our estimated values for our item parameters or our probabilities of a success for each of the observed variables. And we'll try to figure out meaningful patterns and distributions in the classes. So in R, there's a package called the PO-LCA package by Linzer and Lewis. PO stands for Polytomous Variable Latent Class Analysis. It handles both binary and multi-category polytomous indicators, and it uses the EM algorithm with random starts. You can install it with the install packages command. Basically, the argument to this is the following. You have a set of items right here. You tell it your observed variables. And just to keep things simple for this class, we'll just set it equal to 1, meaning we're estimating each of the means. Now, remember, the mean is a probability for each one of those variables. The data themselves fall in a data frame. Now, here's the one catch, though. Each item has to start with 1. The lowest value can't be 0. So for us with binary data, we just have to add 1, switching our 0, 1 data to 1, 2. But we'll remember the difference as we go forward. We tell it the number of latent classes to estimate, and we also give it the number of random starting points. Remember, we have to start this algorithm multiple times to try to figure out what the most likely solution happens to be. And if we want to keep things not verbose, we just tell it turn the verbose option to false. So let's get into an example. Example number 1. This is from a paper by McCready and Dayton called the Mastery Model paper. In the line of research I studied for many years, diagnostic classification models, this is one of the first papers to discuss the same idea. So this is a pretty big paper in my world. I think for a lot of people it's less important, but it is a very popular paper. In 1977, these faculty members who were at the University of Maryland had a 4-item assessment, 4 math items that maybe you'd give in a class like this one. And they took those 4 items and gave it to 142 different students. What they ended up finding were a 2-class solution seemed to fit best. And those 2 classes sort of differentiated students to what they called masters and non-masters. Now, I will note, after years of doing this, the term mastery and non-mastery is a concept that is often used to talk about mastering content in an educational setting, but it's seldom defined well. So a definition that you will see from this is largely arbitrary and post hoc. So some might argue that this is really not demonstrating mastery at all. We're going to see that in just a bit. But those are the labels that were used to describe the 2 classes. So we're going to fit a 2-class latent class model and interpret the results. Here are the data. Remember, the POL-LCA package requires each item's values to be positive integers starting at 1. So for binary items that were originally coded in 0, 1, we'll just add a 1 to each one. And you'll see here, this is the count of people for like the first item who had a 1 and a 2. And the very first set of data, the 2s you see everywhere are people who have answered each item correctly or with a 1. The U is the label for the item in this data frame here. Okay. Here is the output. What we end up having for each item and for each class is the probability a person from that class answers each item, right? So here, for item 1, we see there's two groups: probability of a 1, probability of a 2. Remember, a 1 indicates the item was answered incorrectly. A 2 answers indicates an item was answered correctly, right? We just have to subtract 1 from those numbers. So what this is telling us is people in class 1 had a 20% chance of answering item 1 correctly, and a 75% chance, and people in class 2 had a 75% chance of answering item 1 correctly. So let me say that one more time. People in class 1, 21%, roughly 21% chance of answering that first item correct. People in class 2 had about a 75% chance. So right now we're thinking, oh, class 2, higher chance of answering item correct. We go to item 2, you see people in class 1 had a 6% chance of answering item 2 correctly, while people in class 2 had a 78% chance. Same thing with item 3. And people in class 1 only had about a 2% chance of answering it correctly, whereas people in class 2 had a 43% chance. Now, that's lower than the 70% you see in each of these other places, but this is a little bit harder item, I believe. And finally, people in class 4 had a 5% chance of answering item 1 correctly, or item 4 correctly. People, back this up. People in class 1 had a 5% chance of answering item 4 correctly, and people in class 2 had about a 71% chance of answering item 4 correctly. So that's trying to give us a sense as to how each person from each class would answer, or what chance they'd have of answering each item. Then what we end up getting from this is the probability that a person is in either class overall without respect to anything other than data, right? So what it's telling you is literally there's a 41 of the people in our sample, we think about 41.3% are in class 1 and 58.66% are in class 2. Later in the output, you'll see here, now you'll see the same number by class memberships by modal posterior probability. This is if we rounded each person's probability. It's less precise for what we do, particularly with small numbers of n's. So I don't tend to look at this number right here. And then we get a little bit of model fit information, right? We have 142 observations. We had 9 estimated parameters. What do you say those 9 happen to be? Well, we have 8 right here. 1, 2, 3, 4, 5, 6, 7, 8 probabilities, because within each class, the other term is the complement, right? So we just have to estimate one of these numbers. The other one comes from 1 minus that estimate. And then we have 1 probability for the overall number of people in each class. So there's our 9. We have 6 degrees of freedom. Now, where that comes from is we have to think about in this case, with categorical data and a multivariate model like we have, what we look at here for fit to the data is not like a covariance matrix or a mean vector like you'd see in a multivariate normal. Now, that fit comes for latent profile analysis at the latter half of this lecture. What we're looking at here is the probability a person responds with a given profile itself. So a profile means what permutation of correct and incorrect they have. So with binary data, the number of if we have j items, the number of profiles we have is 2 to the jth power. So with 4 items, there are 16 different ways a person can answer the data in this example. That's 16, the degrees of freedom, we take 16 minus the number of parameters. In this case, that gives us 7 degrees of freedom. Then we subtract 1 off of that. So we get 6. So that's where that degrees of freedom comes from. Here is our log likelihood value as well. And what we can get from this is sort of tests of model fit. We have AIC and BIC right here. Whoa, where'd it go? Right here, AIC and BIC. That tells us relative to other models how well our model fits. When we fit just one model, that doesn't help a whole lot. Now, G squared and chi-squared are absolute model fit indices. These are useful. However, they're only valid when we have small numbers of items relative to the sample we'll have. More on that in just a moment. But both of these we could find a p-value for by looking at this number compared to a chi-square, either of these numbers, compared to a chi-square distribution with 6 degrees of freedom. So I mentioned I went through all of these types of probability. They give you the class size estimates, A to C. That is the proportion in each class. Once again, that is 58.66 in class 1, 41.34 in class 2. We have our item response probabilities. That was each of these 4 numbers that we see up here, 8 numbers we see up here. And then we have our posterior probabilities for each person. I haven't shown that to you yet. So again, this is stepping through each. We see here, I've already done that for each of these. Now, here's where the part gets interesting. How do we determine which class means what? So here we take a look at each of those class-specific item response probabilities. This is the probability of a successful item response for each class. And here are the numbers that you see. And here are the values that you get here. And actually, this label's backwards, of course. The blue term are people in class 2. These are people who have answered with a high probability of answering the item correctly. You'll see in class 2, each of those probabilities for each item is higher than in class 1. So McCready and Dayton called this class the mastery class. Ignore this non-mastery right here. Non-mastery would be class 1. Oh, and that's not going to work. Anyway, non-mastery here is class 1, where you can tell why they called it that is that these students and from this class, if you think of them as being part of this class, have a very low chance of answering each item correctly. In fact, much lower than the students in class 2. So that was where the distinction comes from. Now, again, I'm going to note those labels are arbitrary, right? You could say higher performing or lower performing and just be just as accurate. In fact, I'd prefer that because to be a master of a content area, I feel like you can't really express it very well with 4 items. It's a tough guess as to how to do that. Now, how do we assess model fit? I already mentioned a little bit of that. Right? We have absolute fit tests, relative fit tests, and then classification quality, which is something we call entropy. So the model-based chi-square test itself, this was the chi-square you saw at the bottom, where we're comparing our fit to this number of profiles we have, uses the Pearson chi-square statistic that you might have learned in introductory statistics. In this case, we have what we've observed for each one of our 16 profiles. So with this data, we would go and count the number of people that gave us each profile. That would be observed. And then based on the model equation and our estimated parameters, we can come up with the expected number of people for each profile. We put that in this formula where we take observed minus expected squared and divide it by the number expected. We sum that across each of the profiles, and next thing you know, we have a chi-square statistic. That is how that works. Now, there is a huge limitation in this, and you probably learned this in introductory statistics as well, in that chi-square statistics work great when you have cell counts where numbers of people are quite large. But when you get cell counts where you have very small counts of people in each cell, the chi-square tends to stop working altogether. And so here's an example. With 4 items like we have 16 patterns. 16 patterns versus 144 observations, 142 observations, whatever it is something that is a relatively good ratio. And in fact, if you look at the data, I believe there is at least one person with each pattern represented in our data. However, if we had 20 items, which is not a big ask if you're doing this with a survey or even a test, 2 to the 20th power is over 1 million patterns. So you need a sample size to use this chi-square that was not just 1 million, just hoping people get put into each pattern. You'd have to have it much larger than 1 million because there will be some patterns that are very difficult to observe in practice, given the nature of correlations in the data. So the chi-square test of model fit is valid only in small parts. And this is what in other places with categorical data, we would get into limited information model fit. I'm not going to get into that in this class, but just know that these statistics can only take you so far. Here are the values in R. Forgive the null value there. I don't know why that goes away. This was the chi-square. This is the Pearson chi-square. The p-value is 0.149. The g-squared is a maximum likelihood-based version of chi-square. It follows the same chi-square distribution. And in the limit, as n goes to infinity, they should both converge to the same number. And they're roughly the same here. You'll see that either way, we see the model tends to fit the data. And what we're looking for here is a p-value that basically our null hypothesis is that the model fits the data. The alternative is the model doesn't fit the data. That's one easy way of looking at this. And what you can say is, with that in mind, this p-value being fairly large indicates that our model just tends to fit the data pretty well. So this is a good idea to use. So we'll use the 2-class model. The log likelihood of the model came from, again, our model-based likelihood summed across every observation itself. AIC and BIC take that log likelihood and penalize it by the number of parameters. BIC actually penalizes it also by the number of the sample size itself. And lower values indicate better fit. But in this example, because we only fit one model, we have nothing to compare to. So AIC and BIC don't help us a whole lot here. But we could look at it. Actually, I did do this. I did vary the number of classes. I had 1, 2, and 3 classes. And you'll see here, what we're looking for is the lowest AIC. For AIC, the most preferred would be the 2-class solution. For BIC, the most preferred would be the 2-class solution. It always works out nicely when both agree. That doesn't always happen, though. But it does work out nicely when they both agree. So again, we have evidence to suggest the 2-class solution is the best. And there is that information once again. Now, finally, once we look at the solution, what we can talk about next is how well each observation is classified into each group. So in this case, what we're talking about is for each person, they have a probability they fall under each class. I'm not showing that in this example here, but you can find it in the output. You can find it in the R object. But what we're trying to say is, you can think of it this way. A really separable set of classes would be one where each person gets assigned to one class with probability 1, completely certain that they're in one class, and all the other probabilities for any other class are 0. Right? So for each person, it's very obvious as to which class they fall into. Now, in a lot of data, and particularly when we get to our next example, you'll see this. A lot of our data aren't that clear cut. There may be classes that are hard to distinguish from each other. So entropy is a statistic built to try to measure that. And basically the idea is this. Entropy is interesting because the word entropy means smaller values of entropy in a physical sense means less chaos in the system. M plus and other researchers have sort of turned this around to scale entropy between 0 and 1. They call it relative entropy, where really we want a value of entropy near 1, which really talks about high classification's consistency, certainty, right? Each person clearly belongs to one class and one class only. So you can think of a relative entropy of 1 as being that case that I gave you in the example, where a person has a probability of 1 of being assigned to one class and 0 for all the other classes. So basically, we know they're 100% in one class. We're 100% certain they're in one class. Now, a relative entropy at 0 is the polar opposite of that. Think of it this way. If we have 2 classes, if we basically said each person has a 50-50 chance of being in class 1 or class 2, that'd be a solution that has absolutely no information at all about our data, about our class. So that would give us a relative entropy at 0 itself. So entropy is one way to measure that. So for us, our entropy is 0.754. This would be considered pretty good classification quality. The higher, the better, though. And it's difficult. This is not a statistic that has well-defined cutoffs as to what is good versus not. So this good term right here is just based on my own distinction itself. So that was latent class analysis. Now we're going to follow into latent profile analysis. Now, really, the only difference between latent class and latent profile analysis is the assumed distribution of the observed variables that we end up having. Latent profile analysis will allow for continuous variables, and it's very much like confirmatory factor analysis or regular regression, whereas latent class analysis with binary variables is very much like logistic regression. So, again, in that book by Lazarsfeld and Henry from 1968, latent profile analysis was also described. It uses a set of continuous variables rather than binary indicators. And the estimation process is the same. We use the EM algorithm with multiple random starts. The key difference here is, again, instead of using Bernoulli distributions, with continuous variables, we use a continuous variable distribution, in this case, a normal or Gaussian distribution. So the process, again, is the same. For a specified number of classes, the latent profile analysis will estimate for each class the mean and variance of each variable. And for each observation, the probability of belonging to each class itself. And then finally, we also have the proportion of people in each class. There's the same types of information from latent class analysis. We've got, again, class-specific information, person-specific probability information, and then information about each of the observed variables. Now, I will note latent profile analysis may also allow you to estimate covariances between classes, because in the multivariate normal distribution, you can relax the assumption of local independence, although in our example, we won't. So for each variable, we assume a normal distribution. This is the normal distribution's PDF. It has two variables, mu and sigma squared. This pi right here is the number of 3.14, where pi in our previous example was a parameter. This is just a constant, a number. So for each variable, we'll have a mean and a variance for each class. And the input is, in this case, the person's score or value of that variable, xi itself. Now, different classes may have different means and different variances. And because normal distributions get a little wonky, particularly in estimating variances, you'll see in latent profile analyses a lot of different ways of estimating them such that the variances have constraints put on them. So we might start an analysis where we assume equal variances across classes. And that's because when you get a class that has a small number of people in it, turns out that's like estimating a variance with a small number of people. It's very difficult. It doesn't go well sometimes. So it's much more parsimonious, and it's commonly the default that we see. Although I much prefer the idea that classes don't have to have equal variances. They may have unequal variances. And again, what will determine which model you're using is in part model fit, right? Comparing models with different choices for variances, but also in part whether you can estimate a model with a given number of classes itself. So when you have a bunch of univariate normal distributions, in this case for each of the observed variables, we can also characterize that not with a series of independent univariate normals, but with a multivariate normal distribution. That's what you see here. In this case, we have a covariance matrix and a mean vector describing our variables. And if what we're really doing with a latent profile analysis is estimating a separate covariance matrix or mean vector for each group. Now, if we assume equal variances along items across classes, then this covariance matrix is not estimated as separate for each group. The mean vector almost always happens to be. So in a standard latent profile analysis, again, this is the assumption of local independence, we assume the within class covariance is zero. What that means is that any correlation among our items is fully described by the classes themselves, or the classes of observations are really giving rise to that correlation. I'll show this in the example in just a bit. So basically, we can check whether or not the local independence assumption holds. We could compare classes with and without covariances via AIC and BIC. And whether or not this is violated or not is sometimes, this is less, I would say that in a practical sense, in psychometric analyses, or depending on what you're using a classification for, the idea of local independence is a very strong foundational assumption. But sometimes, we have data that don't really follow it, particularly in latent profile analysis. So I tend to say that the local independence assumption in latent profile analysis is not as fundamental to what we're doing, because we're really not ascribing as much meaning to the class, although in some cases we do. So just note that that's a little bit different here. In fact, we're also going to try a little bit differently as well. So again, if we want to plug this into the finite mixture model, we had our univariate normal. We have a product across all of our variables, and we plug this into this mixture model likelihood where we marginalize across classes right here. We have our mixing proportion of the probability each person falls into one class, the probability a person at random from the sample falls into each class. And then within each class, we have our class-specific variance for each item and our class-specific mean for each item or each observed variable. The tidy LPA package is something that will wrap around another R package called M+. Back in the old days, M+ was a good package for estimating latent profile analyses. The tidy LPA package tries to make it easier. Basically, these are some of the functions that come with the idea of the package. You can estimate models using the estimate profiles or get fit, etc. You can take a look at the example syntax for more information on this. Now, there are different model options for the different classes. Again, the default assumes equal variances across classes and no covariances. But it gets a little bit more complicated as you go further. You can have equal variances across classes and equal covariances across classes. You could have varying variances across classes, but zero covariance. You could also have varying variances and varying covariances, et cetera, et cetera, et cetera. But I will say the more complex models you have, the more parameters get added, and we then use more information criteria to compare the model fit itself. I'll also add that the more complex the model is, the more likely it will not converge, and you will not have a result at all. So let's get into an example. There is a very, very old data set by Sir Ronald Fisher, the man who gave us analysis of variance. He had a data set on measurements from different species of the flower, the iris type of flower. And so Fisher's iris data has been used in examples dating back to the 1930s, almost 100 years old. Actually, it may even be more than 100 years old. I don't know its origin date. I probably could look that up, but I didn't. It's old. Let's go with that. But it does a nice job. Basically, Fisher took 3 species of iris, measured 4 different measurements, physical measurements from them, put that into a data set, and tried to say, can I use a classification method to then go backwards and see how many species of flowers I have? And then once I know how many species I have, what are the characteristics of flowers from that species? So the 4 measurements that he had measured were from 150 iris data. Hey, there it is, 1936. So not quite 100 years old, but definitely 90. Here, sepal length, sepal width, petal length, and petal width. I don't even know if that's sepal or petal. I'm not a flower guy. I don't know how this is, but you can imagine. I definitely know this is the petal length and width, what that is. I have no idea what these parts are, but you can measure them, and he did. So he's got 4 measurements per flower, 150 flowers in total, and they were our 3 different species. And this data set's so well known and applied in so many different classification parts that certain observations in the data set are always the test cases. Like, oh, this one flower, it's the one that seems to have a hard time being classified. How does this new method handle it? So anyway, this is a very famous data set in this area. The 3 different species are Iris setosa, Iris versicolor, and Iris virginica. And we are going to treat the species themselves as unknown and attempt to recover that from the latent profile analysis. So here we estimated a model where we have variances that are equal and covariances are 0. And what we did was estimate a 2, a 3, and a 4 class model right here. And what we'll end up seeing is that the 3 class solution had the lowest AIC, had the lowest BIC. Now you'll note, interestingly, that entropy is higher in the 2 class solution. Remember, entropy being the classification accuracy, but that's because entropy is not a measure of model fit. And often when you underspecify a system, a class system, it may do a better job trying to classify people, but the classes themselves may not be valid. So we don't look at entropy based on model fit, but we will say that AIC and BIC both, actually in this case, favored the 4 class. In this case, actually favored the 4 class solution. Here I am looking at the boldface. AIC is lowest in the 4 class. BIC is lowest from the 4 class. And this is actually a known problem with information criteria and mixture modeling. They often favor over-extraction or more classes than truly exist. These are sometimes called spurious latent classes. This happens almost all the time. And in part, it's because some of the assumptions of our model isn't correct. Remember, in model 1, in this idea, we assume the variance of each variable is equal across classes and that there's 0 covariance among variables within class. Right? So this is not a good, this is a good example of a problem that is well known in mixture models themselves. Here are some results. I'm going to get to those in just a bit. This is also for each flower. These are the probabilities that you end up seeing. These are the cumulative probabilities of being in each class itself. And we also get the class sizes, the proportion of flowers in each class. These are roughly equal, which is what we'd expect for the 3-class solution, because we had equal numbers of flowers. In fact, class 1 had 50. Class 2 and class 3 overlap a little bit more. So here are where we look at the means for each variable, again, trying to determine what it means to be in each class. You'll see in class 1, the sepal length was about 5 centimeters, whereas the width was 3. Compare that to class 2, which is about 6 centimeters and a little less than 3, and then class 3 had about 7 centimeters and a little bit at about 3 for the width. Similarly, with the petal length and petal width, you'll see class 1 had a petal length of 1.46 and petal width of 0.25. Remember, that was the class that had exactly 50 people in it, meaning, or 50 flowers in it, meaning this literally was the very first class. Class 2 had a little bit different measures, and class 3 had a little bit different measures. So what this is telling us is class 1 has very small petals and very wide sepals, which follows the iris setosa variety of the iris. Whereas class 2 had medium-sized flowers and narrower sepals, and that's iris versicolor. And then class 3 had the largest petals and largest sepals, which is iris virginica. So class 2 and class 3, interestingly, are harder to distinguish. And if you look at the reason why is take a look here at petal width. Class 1 is quite a ways away on petal width from the values of either of these, petal length and petal width, whereas class 2 and class 3 are closer, meaning it's harder to differentiate the two, although they still differentiate quite well. Here is an example of these. This is the means for each class plotted with standard error bars for each, and this is the mean. This is a little cluttered, so I made that graph over here as well. You can see each of the differences, and really, what's interesting for each of the variables. Remember, sepal length, sepal width, petal length, petal width. You can see here the distinction. That basically the idea is the closer these dots are, the more indistinguishable the classes are on that variable that you've observed. So in this iris data, what you would see is the sepals themselves are very close together, whereas the petals are very far apart. So it's very difficult to differentiate based on petals or sepals, but petals are really differentiate these flowers. We could also look at classification quality for each class. This is sort of the average posterior probability. This is like entropy, but we're just doing it within. What you'll see here is flowers that were classified into class 1, all were classified into class 1 with certainty. That's why its setosa is perfectly separated from the other flowers. Whereas flowers in class 2 and flowers in class 3, there are a few flowers where we're not certain about. They sort of land on the border between the two. And this makes it a little bit harder to distinguish. So about 3 to 4% of flowers overlap here. And this evidently matches the known botanical overlap between the versicolor and the virginica, although don't ask me the details on that. So that wraps up our lecture on classification using finite mixture models, in particular latent class and latent profile. The differences between the two are solely about the distribution. Bernoulli distributions have one parameter, an item probability, whereas normal distributions have means, variances, and potentially covariances, multivariate-wise. There are many different extensions of these models that exist out there. Growth mixture models try to detect groups with differing growth trajectories over time. Diagnostic classification models, the area that I have done a lot of research in, are confirmatory versions of these models that try to specify class characteristics prior to your analysis. We use them in psychological and educational tests. There are also mixture IRT models that combine item response theory with latent class models. We can have mixture regression models. So do regression lines fit the same for all of your data? And just in general, any finite mixture model, any statistical distribution, any model that's statistically based can be put into a mixture model itself. And it's interesting, you'll see about 20 years ago, the package M Plus did a really good job rolling out mixture models, almost every type of measurement model or other model that M Plus can do, which is quite a bit. And at that time, people got really interested in mixtures. I'd say the interest has certainly died down because of the pitfalls of over-extracting classes. But these methods can be useful in trying to understand your data. So that is why the purpose of this lecture exists. So again, latent class analysis, latent profile analysis are both subsumed into finite mixture models. These are model-based techniques for identifying latent clusters. Both methods make explicit testable assumptions about the data that you have. And there are key practical challenges here. The number of classes must be inferred, right? We have to go fit extra models for each. Information criteria often favor over-extraction of classes. And furthermore, in estimation, there may be local maxima possible, right? So that's very difficult to get around. And I will say these are fascinating models, but use them carefully. They're exploratory and prone to spurious findings. Validate your results with substantive knowledge or otherwise. Seek convergence across multiple fit indices and replicate with independent samples when possible. Here are some references of the material that we covered today as well too. Thank you for listening.